Wait.
So welcome everybody. Today we have Karl Landsteiner and he will talk about how to get from PT quantum mechanics to PT holography. So when you're ready, go ahead, Karl.
Okay, so thank you very much for this kind invitation.
Hey!
Oh, hello.
Please, can everybody mute themselves, please?
Yeah, okay.
The host has to mute everybody.
Okay, so let's start. Okay, so thanks a lot for this kind invitation. That's really a bit of an honor for me because I'm really an outsider to this field. Basically all of you know much more about this field than I do. It's a field which is really exploding, I think, in the last few years, and so I also noticed these developments about usage of non-Hermitian and pseudo-Hermitian Hamiltonians in quantum mechanics and quantum field theory, and I wanted to learn about it. And you know, the best way of learning something is trying to do it yourself. And so the thing I know is holography, and so I tried to combine both and see what I can learn about PT quantum physics from the holographic perspective. So far, I've co-authored two papers on the subject. The first with Daniel Arian and Ignacio Salazar Lander in 2019, just before the pandemics, and then just after the pandemics. There's a new paper with my student Sergio on the net. So now okay. So this is, you know, I'm an outsider to the field, so I don't know the literature fully. And just to give you an impression of what I know, these are sort of the most, the papers I studied probably most. You know, they're this fundamental paper by Karl Landsteiner and Böttcher, and then some reviews and books, and especially this last two, which will be important in the end of the talk, where I do time development, where I learned how to do this time-dependent pseudo-Hermitian Hamiltonians. But if I miss some important references, I ask for excuse because I'm really not an expert in the field. Now, happily, this is not the first encounter between holography and PT symmetry. There is mostly organized by Daniel and his collaborators. We have a similar lecture series, seminar series like this one here about applications of holography. It's called HoloTube. There are videos on YouTube and so on. And some time ago, we asked Karl Landsteiner to teach us about PT symmetry, and we had a talk about this. And I'm very happy to give a talk about holography in the PT seminar series. Okay, so this is the outline of my talk, and I start very basic with stuff which you all know, but which for me is important because it teaches me how to think, or this is how I learned want to think about this in a very, very simple model, and then trying to generalize. So this is the probably simple system of PT quantum mechanics. Then I will spend quite some time on reviewing holography and try to motivate and give a little bit of an impression what you can do, what it's good for, and why people are doing this. And then I will review the results from our holographic model, where we implement this PT deformation of holography. I will study the static properties. I will show that there is also a PT phase transition, put the theory also at finite temperature and discuss its properties. And then the second part will be doing the same thing, but now in a time-dependent setup, sort of a quantum quench in a non-Hermitian direction, where you switch on some non-Hermitian Hamiltonian. And here I will discuss also these different formalisms you can employ and I will discuss a Hermitian, purely Hermitian time evolution versus a non-Hermitian time evolution, and then I will summarize, and throughout the talk I will try to make some points where probably I think we can learn, or where I think I've learned something from doing holography, probably in a wider context and applicable to PT, quantum field theory in general. So here's the most simple system, which I've just copied from, I think I've seen this in a talk from Karl Bender, so there's nothing original here. But it's the way I like to think about it. And so you just look at the particle in a box, and then you describe it by wave function, which is simply, a phase which evolves in time, and then the energy is just a number, and the probability of finding the particle in the box is just 1. But then you can make this a leaky box, and you just go on and do something which I'm not sure if this is really legal in quantum mechanics, but you say the probability, there's some escape probability, and you describe it by some decay rate gamma, and then formally you write down some non-Hermitian Hamiltonian. So, and on the other hand, you can embed this system, this leaky box, into an environment with lots of particles on the outside, an infinite path of particles, and there is a probability that the particle comes in, and now the number of particles is exponentially growing with the growth rate gamma, and so you could say, well, we assign it a wave function like this, and then the Hamiltonian is again non-Hermitian. So by itself, these two systems, these two descriptions probably don't make too much sense from a quantum mechanical point of view. But surprisingly, if you couple these two by allowing the particles to tunnel from box A to box B with a tunneling amplitude G, then you would write down this 2x2 Hamiltonian, which describes the quantum dynamics of this system. This is certainly a non-Hermitian Hamiltonian, but surprisingly, the energy eigenvalues are real as long as the tunneling amplitude is large enough compared to the escape rate. So, and as far as I understand, this is sort of the paradigmatic example of this what PT Hamiltonians mean, namely that they describe open quantum systems with an exact balance between source and sink. So here the basic features, what this PT symmetry is. So it's a time reversal symmetry combined with parity. So time reversal symmetry in quantum mechanics is just complex conjugation, and parity exchanges these two boxes. And the symmetry, so it's a symmetry, it commutes with the Hamiltonian and squares to 1. And this has the effect that if the eigenstates of the PT operator, then the energy eigenstates have to be real. And this is in fact realized in this PT symmetric regime where the tunneling amplitude is large enough. Or the energy eigenstates have to come in pairs with complex conjugate energies. And that happens in the so-called PT broken phase when the tunneling amplitude is smaller than the escape rate or the entrance rate. And in between that, there is this PT phase transition. Okay. So that's something we want to copy or also see in how this works in holography. And a useful way of, a slightly different way of understanding this is what I would call a symmetry perspective, where I start again with a simple two-state quantum mechanical system. And every such two-state quantum mechanical system can be written as a linear combination of Pauli matrices with some vector of couplings G. And then any two theories, they are related by a certain rotation, right? So I could start, for example, with a Hamiltonian, which has just the sigma x coupling switched on, and then you could rotate around some axis. Here it's, I think, the y-axis, and generate this new Hamiltonian. And of course, both Hamiltonians, the original one with G prime and this transformed one, rotated one, they have the same spectrum. And so one way then to generate this PT Hamiltonians is to take this transformation matrix and analytically continue it. Take the parameter of the rotation and make it imaginary, do an analytic continuation in this parameter, and then generate the non-Hermitian Hamiltonian. And a somewhat So this is still, you can implement this directly on Hilbert space, where the operator, the rotation acts on Hilbert space. But an equivalent way, and more useful for what I want to do in holography later on, is to implement this transformation directly on the couplings. So I could either implement the transformation on Hilbert space, then it acts on the matrix, and G is just constant, or I take this starting vector of couplings, and I could do a rotation on the couplings and generate the same Hamiltonian. And of course, again, I could go to the non-Hermitian one by doing an analytic continuation. So this I've done here. So here's the same thing. Now the transformation matrix is not the unitary matrix, but the Hermitian matrix. And the new Hamiltonian I get doesn't have the sign here, but the hyperbolic sign. And of course, this then is not Hermitian, but it is pseudo-Hermitian, which means that it's conjugate by a Hermitian matrix to a Hermitian Hamiltonian, which I denote by lowercase h. And then we can also understand why this tunneling amplitude G, right? G now, this tunneling amplitude I had before is given by G prime times the hyperbolic cosinus, and the escape rate or growth rate is given by the sinh. And now it's clear that whenever I do such a transformation, then that will the tunneling amplitude will always be bigger than the escape rate. So I'm always in this PT broken regime. And the energies there, of course, real then. And of course, with such a transformation, I can never go to this PT broken regime. So, and to my understanding, there's a one-to-one relationship between having a Hamiltonian, non-Hermitian Hamiltonian in the PT symmetric regime, and there always exists a transformation matrix eta, which allows you to transform back this non-Hermitian Hamiltonian to a Hermitian one. So, and here I've just collected some of the features of this pseudo-Hermitian quantum mechanics. So again, I said it's conjugate in the PT symmetric regime. It's conjugate to an Hermitian Hamiltonian by a Hermitian matrix. Then you can have left and right eigenvectors. Probably the most important thing here is that the metric on Hilbert space now is non-trivial. It's not just the unit matrix, but it's given by the square of this transformation matrix, eta squared. But if you define your inner product in Hilbert space with the help of this metric, then you can actually show that the Schrödinger equation based on the non-Hermitian Hamiltonian generates a unitary time evolution. So if you compute how the inner product given between two vectors in Hilbert space with this metric eta squared changes in time under the time evolution generated by h, the non-Hermitian Hamiltonian, then you find it's indeed unitary, and the norm or inner product of two vectors in Hilbert space does not change. Okay, so that's just a quick review of PT quantum mechanics. And of course, you can do this also in quantum, well, of course, but certainly much more difficult issues. But a very, very simple way of doing something like this in a simple-minded way, probably to do this in quantum field theory is, again, you could pick some operator which transforms under some symmetry. So here, for example, I'm thinking of a quantum field theory which has of spinors, which has a mass term, psi bar psi. And then if this is, say, a four-dimensional spinor, there is a partner axial mass term, which is I psi bar gamma 5 psi. And these two transform into each other under a chiral rotation, which is a rotation, a U1 rotation, which is generated by gamma 5. And you could build this complex linear combination of these two operators, and this operator is an eigenstate of this transformation. So it has charge 2 under this axial U1. And then you could go and generate a non-Hermitian theory just in the same way. You could take a coupling, original mass coupling M, and do some transformation with this transformation acting on the couplings and analytically continue in alpha to some imaginary value alpha hat. And then you would generate a theory which has the usual Hermitian mass term, but it also has this non-Hermitian mass term with M5 without the I here. So again, it's a non-Hermitian operator. And if you calculate, at least in the free theory, it's easy to calculate the spectrum of this theory, and the spectrum is very similar to what we had before. It's momentum squared, but then it's this Hermitian mass term squared minus the non-Hermitian mass term squared. And again, you have that this spectrum is real whenever, as long as M5 is smaller than M0, the Hermitian mass. So it's so this is a very simple quantum field theoretical model, which also implements this PT symmetry. Okay, so this is all not new to you. You know all this perfectly. Now comes the new stuff, the ingredient, which I'm adding, and this is holography, also known as the gauge-gravity duality. So the holography is based, the basic ingredient of this is a space-time, which is anti-de Sitter space-time, or asymptotically anti-de Sitter space-time. Here I've written down the metric and a specific coordinate patch. You see that basically it's flat space, which is just Minkowski space minus the t squared plus the x squared. And then this flat space is fibered over into radial direction r, which runs from 0 to infinity. And it grows like r squared as you go out with r to infinity. Such a space has constant negative curvature, it's maximally symmetric, and the isometry group actually is precisely the conformal group of this Minkowski space. So if you check, for example, you can see this by rescaling the t and the x coordinate, and at the same time rescaling in the inverse with the inverse the r coordinate, and this metric is invariant, so it has a scaling symmetry, and more generally it has realizes the full conformal symmetry. And it also has something which is called a conformal boundary, where formally you go with r to infinity and divide by a function which goes like 1 over r squared at infinity. And that generates not just the flat space, but it generates a conformal structure, conformal, or say the conformal compactification of Minkowski space. So naturally, you have a conformal structure in the field in this theory, in this geometry. And so the original conjecture comes from string theory, where a particular kind of string theory, type 2B string theory, which of course, like string theory, all string theories have to live in higher dimensions, in 10 dimensions. And here the anti-de Sitter space is just part of space-time. It's the non-compact part, 5-dimensional anti-de Sitter space. And there is an additional 5-dimensional compact space, a 5-sphere, which for our purposes we can forget about. What it encodes is the internal symmetries of the theory. So it's an SO6 isometry on the S5, and this plays the role of the internal symmetries of the quantum field theory. And so the original conjecture is that this type 2B string theory on spaces which are asymptotically ADS5 cross S5 is exactly equivalent to maximally supersymmetric gauge theory in 4 dimensions. So maximally supersymmetric gauge theory is a unique theory. The matter content is completely determined. It consists of a gauge field, 4 gauginos and 6 scalar fields. You cannot add anything more to it. And it can have just a gauge group of rank n, nc. And then the map from the string theory variables to the field theory variables is given here. So you form this product of the gauge coupling times the rank of the gauge group, this 't Hooft coupling, and this is proportional to, this anti-de Sitter space has an intrinsic length scale, which is inverse to the curvature. And you take the ratio of this length scale to the string tension. So the only input parameter in the string theory is the tension of the string. And this dimensionless number you can interpret as the 't Hooft coupling of the dual field theory. And the inverse of the rank of the gauge group is proportional to the string coupling, which describes the joining, the amplitude for joining and splitting a string, like it's depicted here. So in this way, you can map the expansion of string theory, which is an expansion on the world sheet conformal field theory given by this parameter here, and then an expansion in terms of the string splitting and joining amplitudes given by this. And this can be mapped exactly to the large N 't Hooft expansion of this supersymmetric gauge theory, at least formally. But what is important here is that if this duality holds, and there are very good indications, probably not the proof, but it's very strongly believed that this holds, that it's a strong weak coupling duality. That means when the gravity description, so these are exactly the same theories, just in a different language. And when the theory, from the field theory point of view, is at very, very, very strong coupling, very strong 't Hooft coupling, so this product being very, very large, then this is very, very small. And then the string theory is a good description. And at the same time, when the rank of the gauge group is very, very large, then this splitting and joining is very rare. And so you can give it a perturbative string expansion. So it's a strong, weak coupling duality in the sense that every time when the field theory runs into a regime which is very, very strongly coupled, the string theory or the gravity theory is very weakly coupled, and you can do perturbative gravitational calculations. Okay, so here's more in detail. The original idea of this so-called holographic principle, because it's holographic because it maps the 5-dimensional anti-de Sitter space to a 4-dimensional, 5-dimensional quantum gravity to a 4-dimensional quantum field theory. And the ideas go back to ideas about quantum gravity in general, where the observation is made that if you have a black hole in gravity, then the entropy, which is already something which you have to compute using quantum mechanics, quantum field theory, the entropy of a black hole is proportional only to its area and not to its volume. So this has given rise to the idea, I think first spelled out by 't Hooft and then later promoted by Susskind, that in a theory of quantum gravity, the number of degrees in a certain volume is bounded by the area which actually bounds the volume. So there cannot be, so there are no volume degrees of freedom. There are only these sort of surface degrees of freedom. And this holographic principle, as it appeared in this type 2B string theory, motivated from string theory, is a direct realization of this principle, where the whole theory in the bulk, in this ADS5 space-time, this quantum string theory can be mapped to a theory which lives in 1 dimension less on the boundary, on this conformal boundary, is a conformal field theory, and it's precisely this maximally supersymmetric field theory. But I think the general principle is, even if you believe that, there are other ways of quantizing gravity, and that string theory is not the unique way of quantizing gravity, I think it is still true that this insight would hold in every quantum theory of gravity, that's the right way of how to view quantum gravity with asymptotically anti-de Sitter space, in the sense that whatever you calculate in asymptotically in quantum gravity, where you keep the boundary conditions fixed to be asymptotically anti-de Sitter, if you can, whatever quantum theory you have, which calculates this path integral, it would be interpretable in a dual way as a quantum field theory living on this conformal boundary. And the precise map is, if you have a quantum field theory, so let's think again about our this Dirac mass term, psi bar psi, and you switch on this mass term, then you have a coupling, a mass term, but here we want to make it more general. So we think about the space-time dependent mass term. So then it's really profitable to think of this as a source for the local operator, which is psi bar psi at x. And if you add this to your action and to this field theory integral, then you would generate a functional which depends on the source term, which is a classical function. And if you do, and at the same time, in the gravity theory, you keep the boundary conditions, these conformal boundary conditions fixed, and identify the boundary term of an appropriately chosen scalar field with this mass term or with the source term for this operator. Then the statement is that if you can do this integral and this integral, these two have to be the same. So So here it's more a little bit more in detail for a scalar field. So you can study, of course, in practice, what you do is you do this in a sort of semi-classical approximation. You solve classical field equations and plug them in a sort of saddle point approximation and plug them into the classical gravity action. And this should be a good approximation when you are at this limit of infinite coupling in the dual field theory. So you can study what happens, for example, in the simplest case, when you have a scalar field, you solve the scalar field equation in anti-de Sitter space. Turns out that there are two solutions, two modes, which have an asymptotic expansion for r equals infinity, which looks like this. Delta plus minus these exponents are given by the dimension of anti-de Sitter space, the curvature radius, and this is the bulk mass term. So this is a mass term which lives in the scalar field. I should have chosen a different letter here, I'm sorry. And then you generate this, you plug the solution into the on-shell action, and you interpret this as a functional which depends on this boundary value, which goes with this delta minus, which is the smaller exponent here. Because it turns out that if you calculate, say, the energy of such a mode, it turns out that this leading mode, the first solution, has an infinite energy, whereas this has finite energy. And that means that in your path integral, if you fix this mode, this cannot fluctuate. You keep the boundary condition fixed, but this guy can fluctuate. And in terms of the solutions, it means that this solution you can determine just from the boundary data, but the subleading solution, you have actually to impose boundary conditions also in the interior to really determine what's the value of this phi 1 field, that's, so to speak, the dynamical information. And so you generate this functional dependent on your boundary values or your boundary function, phi naught of x, and then you vary with it, you treat it like the source for an operator, and it turns out it just spits out this subleading coefficient phi 1, if you do this, say, up to the quadratic level in fields. And this you interpret as the vacuum expectation value or the expectation value of an operator in a dual field theory. So this is the essence of the holographic dictionary. That tells you that choosing boundary values for the fields in anti-de Sitter space and then calculating this generating functional function, and you interpret this as a generating functional for Green's functions. And if you do this in a more general way, that allows you to calculate correlation functions of a field theory, a dual field theory, which lives in one dimension less, right? Because the boundary conditions, of course, they don't depend on this additional r direction, this holographic direction. They just live in 3+1 dimensions, or 2+1, or whatever is the dimension of the field theory you are interested in. Okay, so here again, here is this holographic dictionary, more schematic. So for every field in your gravity theory, there is a dual quantum field theory operator. So, and this applies even to the metric itself. So if you study the metric and you allow the metric to fluctuate a little bit around its background value, then you can calculate in the same recipe correlation functions and vacuum expectation values of an object which behaves just like the expectation value of an energy momentum tensor in a quantum field theory. You can actually show explicitly that with this recipe you can reproduce the Ward identities which are valid for an energy momentum tensor in a quantum field theory. And in the same way, if you study a gauge field in anti-de Sitter space, so it's not just gravity, it's gravity plus a whole bunch of additional fields, gauge fields, scalar fields, fermion fields if you want. And so for a gauge field, this similar statement holds. It's a spin 1 field, so it has one index, and it's actually dual to a conserved current. And again, you can show that the gauge symmetry that lives in this 5-dimensional anti-de Sitter space can be reinterpreted on the boundary with this holographic recipe as the conservation law of a current, a noether current in a quantum field theory. It has exactly the same form. And then you can add additional fields like a scalar fields and so on. Yeah, that's important to notice here that the asymmetry in a quantum field theory, like for example, translational symmetry in Minkowski quantum field theory, that translates actually into a gauge principle in anti-de Sitter space. So, or if you have a U1 symmetry in your quantum field theory, that translates to having a gauge field like a Maxwell field in anti-de Sitter space in one higher dimension. Good. So again, you can, and then you can extend this dictionary, and you can, as I said, always, you demand asymptotically anti-de Sitter boundary conditions, but not that the space itself is anti-de Sitter. So there are different solutions now. And for example, here's an asymptotically anti-de Sitter Schwarzschild black hole that has this blackening factor, which vanishes at the radius RH, which is actually the horizon of the of this anti-de Sitter black hole. And from Hawking, we learned that actually black holes radiate at a temperature T, which is given basically by the horizon. And if you apply this recipe to spacetimes which contain this black hole, then indeed you can show that you generate correlation functions which have all the properties which you would expect correlation functions of operators in a field theory at finite temperature. So you can check things like KMS condition, etc. So and all these things hold by the magic of having a black hole in the interior of this asymptotically anti-de Sitter space. And that allows you to compute interesting things like response functions, like conductivities, Kubo formulas. It has led to a lot of insight into transport theory, into effective theories like hydrodynamics, the effective long wavelengths. If you study perturbations around such an anti-de Sitter black hole metric, then you find that the long wavelength limit, the low energy limit of these perturbations is actually governed by a theory which is relativistic hydrodynamics. So you can rediscover relativistic hydrodynamics by studying anti-de Sitter black holes. And in fact, indeed, there have been discoveries which have not been known before studying anti-de Sitter black holes. So in particular, one example I worked on a lot was this anomaly and anomaly-induced transport in relativistic hydrodynamics, and that was even by experts in hydrodynamics. It was rejected at first and said that these terms are wrong, they cannot be there for several reasons, but in ADS, applying this recipe, these terms come out uniquely, and then later it was understood that it's actually really a real feature of hydrodynamics, and independent of this holographic dictionary and realization, but it's sufficiently universal that it applies to all field theories. So it's in fact, this has led to quite some discoveries in subjects like hydrodynamics and transport theory. And one spectacular or very, very big success story was the calculation of the shear viscosity, so that you can compute by this holographic recipe I told you, switching on some gravitational fluctuation. So basically what you do is you study gravitational waves in anti-de Sitter space in a specific kinematic regime in a black hole background. And that allows you to compute this correlator by applying this recipe. And this correlator allows you to calculate a transport coefficient, which is a transport coefficient for the dual quantum field theory at finite temperature. And it's particularly here, it's the shear viscosity. And it was shown that it takes this universal value of h bar over, the shear viscosity to entropy ratio takes this universal value, h bar over 4p kb, Boltzmann constant, and h bar Planck constant. And then people used this value and did the hydrodynamic simulations for the quark-gluon plasma and compared it to data. So here's a plot. All right, so what people do is they smash in this, say, relativistic caviar ion collider or at the LHC heavy ions against each other, and they create a new state of matter where the protons and the nucleons melt and create a plasma of quarks and gluons. And this plasma then expands, and this expansion has to be described in a hydrodynamic theory. And the key parameter in this hydrodynamic expansion is the shear viscosity. And this is very, very difficult to compute in QCD. You cannot compute it perturbatively because perturbation theory is only valid at extremely, extremely high temperatures which cannot be reached in experiment. On the other hand, it's a transport coefficient, so it has something to do with real-time evolution, and this is almost impossible to do in lattice field theory, lattice gauge theory. So then this holographic theory, that this calculation is very easy. Of course, you're not studying QCD, you study some theory which has some properties of QCD, like it's a non-abelian gauge theory, it's a strong coupling and so, but you get the value, and people just took this value and compared it to experiment, and here is one of these publications which compared various values of the simulations of eta over S to the experimental data, which are the black dots. And you can see here that the simulation with this holographic value of shear viscosity to entropy ratio actually fits the data very well. So that was quite surprising that the nuclear physicists liked this holographic string theory inspired calculation and took this very serious and it's still one of the best examples where this holography really had input on real physics. But you can ask other things, like for example, you can think, well, basic phenomenon in quantum field theory is certainly spontaneous symmetry breaking, and you can ask, can you do spontaneous symmetry breaking in this holographic setup? And in fact, it turns out you can. And this was done by these people here, Hartnell, Herzog, Horowitz, and they constructed something which they call a holographic superconductor. It's more like a holographic spontaneous condensation of a scalar operator. You can show that such a theory has infinite conductivity. You can check that there is a second sound. You can check the Landau criterion for superfluidity, etc. And the way to do this is you have to calculate what are called quasi-normal modes in this anti-de Sitter space. These are fluctuations around the background, but around the given background in your fields. And the boundary conditions for these fluctuations are that they actually zero at the conformal boundary, but on the black hole horizon, they are purely infalling, because of course you want this thing to be a black hole, meaning that things only fall into the black hole but don't come out. And now it's the first time that we have something non-Hermitian in holography, because the differential equations which you have to solve then, they are of Sturm-Liouville type, but due to boundary conditions, these infalling boundary conditions, they are non-Hermitian Sturm-Liouville problems. And as a result, you get complex frequencies. So these frequencies then tell you that in such a quasi-normal mode, it has a real frequency, it vibrates with some frequency omega, but it of course falls into the black hole, and the rate with which it falls into the black hole is given by the imaginary part. And so here, for example, is from one of our publications where we look to this spontaneous symmetry breaking mechanism, and we followed one of these from the symmetric phase, where no symmetry breaking happens. We followed one of these quasi-normal modes as a function of temperature, and as you lower the temperature and as you go into the regime where the scalar operator wants to condensate, this imaginary part moves over to the upper half plane, and instead of exponentially decaying, now it becomes an exponential growing mode and signifies an instability and tells you that this scalar field operator wants to condense. And of course, in the real world, these quasi-normal modes are quite famous in real black hole physics and in gravitational wave physics, where they describe the late time ring down of these black hole mergers. So just as a side remark. Okay.
We have a question in the
yes,
chat.
Sure.
Maybe Frida, you want to ask it?
Yeah, well, suddenly there comes the word holography. I mean, I can follow everything to the black hole and to superconductors, but what makes this thing holographic? I mean, why do you enter this term? I don't see anywhere holography at the moment.
Yeah. Okay. So here, what I have, so I'm not writing this down, but all of these calculations, all of these, they are done in this setup. You have a 5-dimensional anti-de Sitter black hole, and you study fluctuations around the background of various fields, and you look how these fluctuations behave. You look to their spectrum, like their frequency, and since there's a black hole, all fluctuations fall into the black hole eventually. So the frequency is a real and an imaginary part, and so in this sense, you apply this holographic recipe I outlined before, how you calculate these correlation functions.
Yeah, but what do you mean with holography? I mean, holographic. When I thought of holographic, you look at the phase of some waves, and you can somehow think of this three-dimensional behavior of things which are somehow safe in lower dimensions. But here you could say holographic recipe, but for me there is no holography at the moment. Only so you have a reduction of dimension.
No, that's important. It's not a reduction of dimension. That's a very important point. So this should not be confused with a dimensional reduction. That is certainly not the case. So you have to take the 5-dimensional theory, solve the 5-dimensional theory in full glory. Don't reduce the theory to 4 dimensions. This is not what it is. You have to calculate the 5-dimensional theory, plug the solution of the full 5-dimensional theory into the action, and then how you calculate this. You calculate the solution as a functional of the boundary conditions. And it's these boundary conditions which make the theory holographic. So what you have information about is, you think it's a little bit like being an experimenter. What can you do? You can probe your system by applying some external sources to it, right? You apply some field to it and look how it reacts. And here in holography, we have this anti-de Sitter space. We have no control what is going on inside anti-de Sitter space. That's its own dynamics. I mean, we have to solve these equations, but we have to solve these equations under certain boundary conditions. But we can choose the boundary conditions. So, and then we look how the system reacts according to what boundary conditions we impose on it. And this can be reinterpreted as correlation functions of a quantum field theory in one less dimension. And in this sense, it's holographic because the quantum dynamics of the 4-dimensional quantum field theory is encoded in this gravitational dynamics of the 5-dimensional theory. But it is important that it's not dimensional reduction.
Yeah, in this sense, I understand it, but thank you.
Okay. I mean, this is, if you're, okay. Okay. So now let me come to this holographic model for a PT quantum field theory. So I start out with this action. I've chosen 4-dimensional anti-de Sitter space. So the theory will be dual to a 2 plus 1 dimensional quantum field theory, living in 2 plus 1 dimensions. And so here's the field content. This is just a metric. So lambda is the cosmological constant, which imposes this asymptotically anti-de Sitter boundary conditions on the metric. I have a scalar field with a phi to the 4 interaction, and then I have a gauge field because I will need a symmetry as well. I told you before that symmetries are mapped, Noether currents are mapped to gauge fields in this 5-dimensional anti-de Sitter space. And boundary values are mapped to couplings. So here I have my scalar field, and I can do this expansion. So phi is my boundary value, and O would be eventually the expectation value of the operator I want to calculate. The boundary condition I can impose by hand. This thing I have to calculate. So in Hermitian theory, I would demand that the phi and the phi bar, so this is a complex scalar field, which is gauged and transforms it's gauged under this gauge field. So this is a covariant derivative with a gauge field, which has its own action, f squared here. So since this is a complex scalar field, I can just choose the usual boundary conditions of phi naught being some value, m, It's basically like our mass term for a Dirac fermion, and phi bar being the same one, right? So they have to be complex conjugate to each other. And now any other Hermitian boundary condition can be generated from that one by doing a U1 transformation. I have this gauge field and I can do a U1 transformation on it. And then it would generate by gauge transformation an equivalent Hermitian theory. So for example, I could multiply phi naught by a phase, e to the I alpha, and phi bar by the opposite phase, e to the minus I alpha. That would just be a U1 transformation of the same theory. However, I know for going to the non-Hermitian theory, to this PT theory, I have to do an analytic continuation of this symmetry transformation. And so now I'm doing something which from the gravity perspective, you know, sounds totally crazy. I take the boundary value for the complex field phi and demand that it's m prime times e to the alpha. But for the complex conjugate, I demand that it's m prime times e to the minus alpha, because that's the analytic continuation of this U1 transformation. And then I just want to parameterize it like this. Now I say, well, these are just two arbitrary numbers, real numbers, and I parameterize them differently like this with the parameter psi. And I do this because then in this parameterization, as we will see, this PT phase transition sits precisely at psi equals 1 or psi equals minus 1. So that looks crazy. I have actually the equations and the action for a complex field, but I impose boundary conditions such that these two fields, the boundary conditions, are not complex conjugate to each other. And that's consistent with this philosophy that I can generate a PT symmetric Hamiltonian from a Hermitian Hamiltonian by doing a Hermitian, by doing an analytic continuation of a transformation, which transforms operators into each other. Like in this simple quantum mechanical system, I had this vector of couplings J, and I did a rotation, or then I did a hyperbolic rotation and generated this non-Hermitian Hamiltonian. And here, this is exactly the same principle. The important ingredient is the holographic ingredient that the couplings of the dual field theory are the boundary values of the fields. So everything I have to do is, in order to generate the PT holographic model, is do this non-Hermitian transformation, this analytic continuation, and the symmetry transformation on the boundary values. Okay. And you can check, I mean, here I've worked out how the PT symmetry works on these fields. Okay, there's nothing, you can just work it out. It leaves the action invariant and it leaves this boundary conditions invariant. So indeed, imposing this boundary conditions in that way, you generate some system which has this PT symmetry, right? And then the idea is, instead of doing quantum theory, I'm doing gravity in one higher dimension, and it effectively resumes the quantum theory of the dual field theory. So let's see here, this is detailed, the ansatz for the metric, and so let me, the first thing you do is you just study the vacuum. There is no black hole, and you just impose these boundary conditions and look what the symmetries, what these solutions are doing. And what you find is the solutions are domain walls which interpolate between an asymptotic anti-de Sitter space at r equals infinity. And very much in the interior, as you go with r to 0, you encounter a different anti-de Sitter space. So it's an interpolating domain wall solution which interpolates between two anti-de Sitter spaces. And asymptotically, the scalar field on which you impose this boundary condition wants to go to a fixed value, and this value is given by this thing here. So don't worry about the minus sign in mass term, but it turns out that a scalar field in anti-de Sitter space can have negative mass. It's actually necessary. So because it's not just a constant field, it always will have some modulation in this r direction in anti-de Sitter space. Negative masses are allowed and actually necessary. So this minus m squared is actually a positive number. V is the self-coupling of the scalar field. That's also positive. And that's the value the scalar field wants to take as you go with r to 0 if you impose these non-Hermitian boundary conditions at r equals infinity. And there you see that everything's okay. It's a real value as long as psi is bigger than 1 or bigger than minus 1 or smaller than 1, right? But then if it's outside this region, then it becomes complex. And this complexity actually translates back into the full solution. So you cannot solve anything anymore. You don't find a real metric. If you go beyond this psi equals 1 and you solve the gravity equations, you can still do it, but you find two complex conjugate solutions for the metric. And we interpret this as the holographic analog of the PT phase transition. So if you go beyond this psi equals 1 boundary, you find complex metrics, which two solutions which are complex conjugate to each other, just as you would expect from the simple theory. Now, something quite interesting is happening if you go to these black hole solutions. You take a black hole, you impose these boundary conditions on the scalar field, and then you study what solutions you get. So I call that, sorry, in the plots, the parameter which controls the non-hermiticity is called X, but it's this psi parameter. So the blue line here is the zero temperature and solution, and this simply just stops at psi equals 1. There are no more real solutions beyond psi equals 1. But if you're at finite temperature, surprisingly, you can go beyond psi equals 1 and you find real solutions, and you find actually some complicated structure where there is not a unique solution, there are two real solutions. So this is really quite confusing. So does this mean that finite temperature stabilizes somehow the PT phase transition here, and you can go into this PT broken regime? And the answer is no, because you have not only you do not study, you have also to study not only the background solution but also the stability, and for this you have to study how small fluctuations behave, and for this you have to precisely study these quasi-normal modes. And it turns out that universally for all temperatures, precisely at this point, this exceptional point, psi equals 1, there is a quasi-normal mode which always sits precisely here, independent of the temperature. So here it starts out, that's the Hermitian theory. Then you switch on the non-Hermitian deformation with this psi parameter. And as you reach psi equals 1, at finite temperature, you still have a real metric. All the solution is real. But now this mode moves up to the upper half plane and becomes an instability. So there is an exponentially growing mode. And we spent quite some time to see if something similar happens as for this holographic superconductor, where eventually the mode grows, but then nonlinearities settle in and you get some new solution, some different solution. But here we didn't find that. So apparently this mode wants to grow forever and it never settles down to a new solution. So we interpret this as being the PT phase transition at finite temperature. So also the solution looks real, the fluctuations are unstable about it. And okay, forget about this for a moment, but I can even motivate this behavior from quantum field theory. So if I think about an interacting quantum field theory, usual quantum field theory at finite temperature, then it's a well-established fact that every, say, you take a Dirac field as before and has some self-interaction or whatever, and you start out with a theory with this non-Hermitian theory. You have a usual Hermitian mass term and a non-Hermitian mass term. But at finite temperature, generically, you generate also a thermal mass, which typically goes like self-coupling and T2 squared. And if you plug this in here and then you switch on the temperature, then you see that it looks as if the Hermitian mass becomes larger. And that would mean that the non-Hermitian mass can be also larger. And so just from this formula, by assuming that you generate the thermal mass, you would get the same conclusion that you can go at finite temperature, you can go further into the PT broken regime. But again, I think this will not be the real answer. You should also study these fluctuations, and you should discover that there's an instability in these fluctuations as well. This is something which in principle can be done in weakly coupled quantum field theory, and is, I think, a lesson that can be learned from holography, because the point is that these type of calculations are comparatively easy, even if it involves solving Einstein equations in 5 dimensions in asymptotic antecessor, which is complicated by itself, but it's not as complicated as doing real quantum physics of a quantum field theory, one loop thermal masses, and especially computing fluctuations and poles of propagators where you would see this instability. But in principle, this calculation can be done, and it should give this result that also you generate the thermal mass, the fluctuations still become unstable precisely at the PT phase transition psi = 1. Now that's a sort of prediction from holography, if you want. Now, I'm already quite late. Probably, how much more time can I?
How much do you need?
Probably another 5 minutes to.
Go ahead. Go ahead.
Okay. Yeah. Okay. I will try to get it into 5 minutes. So now the other thing you can do is very nicely, which you can do very nicely in holography, is making this psi parameter time dependent. Now, if you do that in just quantum mechanics, and what this means is you make this eta transformation matrix time dependent. And if you look now to the inner product with this eta squared metric, then you pick up this term, and the inner product is not Hermitian anymore, right? So this is, well, our host, Andreas, and most of us today, there are some reviews of this where I learned about how to deal with this. And in principle, there are two options, which I can both implement in holography. The first option is just live with it, go ahead, just buy the non-hermiticity and see what's going to happen. And the other thing is try to repair the non-hermiticity. And in fact, it's possible. You can repair the non-hermiticity by introducing a gauge field in your Schrödinger equation, which just compensates this term of the non-conservation of the inner product. And this gauge field then is again given by the time, by this formula, basically by the time dependence of this transformation matrix, right? And also Maxine and Peter, they had a recent paper where they studied more consequences of such gauge fields in quantum field theory, non-Hermitian PT quantum field theory. And in holography, I can do this perfectly as well. So what's the interpretation of this? So my interpretation, I go back to this very simple model with two boxes. Interpretation for me is what you do is in this time-dependent context, you change the opening of the box. You make it bigger or smaller. This is like changing this eta transformation matrix with time. But if you just do that, then of course the particle needs some time. It comes in and then it's done lower and then it goes out again. And in between this changes. So this will not be in an equilibrium situation. And therefore you will have some non-Hermitian evolution. On the other hand, if you calculate what's this gauge field, which you have to switch on for getting it Hermitian again, that gauge field is an off-diagonal term. It's like the sigma y matrix. And what it effectively means is that you have to change this hopping parameter in a non-Hermitian way. So the forward hopping and the backward hopping are not the same anymore. If you induce, if that's a way of how to interpret this, this gauge field that you have introduced. And that just compensates for this delay the particle needs to enter and come over and get out again under changing, you know, under time varying these openings. So that's my interpretation of what this gauge field means. Okay, and in holography you can do that. You can do both things. You can just change this psi parameter with time at will. That's a boundary condition, and you can choose that at will. And you can also introduce this gauge field. Again, that's a boundary condition for the gauge field, and you can introduce this. What happens is if you write it like this, the gauge field you have to introduce for getting to Hermitian time evolution, you see as a singularity precisely as you approach the exceptional point. So it means you can come from the PT symmetric regime in the Hermitian theory, but you cannot be beyond it. But here there is, interestingly, no problem going beyond the PT. So if you, okay, so these are the equations. You solve them numerically with these time-dependent boundary conditions. And here, for example, I show the results for a quench, which takes the Hermitian theory to some point in the non-Hermitian theory. And while we have not introduced the gauge field, in between at t equals, in between when this psi parameter varies, the theory is non-Hermitian. And you see this by some Hermitian operators, which you would think are Hermitian operators, have imaginary expectation values. And you also see this in this black hole in a very weird way. You throw stuff into the black hole, but the black hole becomes smaller with these weird boundary conditions. So it violates what is called the null energy condition in gravity. But okay, it's just doing it for some time. And then eventually it settles down to a nice equilibrium state, which again is a PT symmetric situation. So although the system goes through a heavily non-Hermitian time evolution in intermediate times, it settles down to a nice PT symmetric end state. You can do this, you can run into the exceptional point, look what's happening here, don't have time to go into the details. You can also go and make excursions into the PT broken regime. So you crank this parameter xi for some finite time above 1. So you start, say, at xi equals 0.8, which is nicely in the PT symmetric regime. And you crank it up, go beyond 1, stay there for a while, and come back again. So this is the evolution of the xi parameter. And you stay longer and longer in this PT broken regime. And as you see, some of the operators, they want to grow exponentially. But of course, if you stay finite time, it grows for some time and then you come back. So you can, even for some finite time, you can make excursions into the PT broken regime in this setup. On the other hand, you can do this full Hermitian formalism where you also switch on the gauge field and then you can do two things. You can do the time evolution with this full formalism with the gauge field, or you can transform back to Hermitian theory, to the Hermitian time evolution, and then transform back at every time step t, just with this transformation matrix eta. So there are in principle two different things you can do, but of course they should be the same. And in fact, here we show the results of our numerical simulations done in this both different ways, and the points are, I think, the one, the Hermitian evolution, and the other one is this PT evolution with the gauge field, and you see they give exactly the same results. So it's exactly consistent. Okay, so in a way, here what this tells you is that if you introduce this gauge field in addition, what you're doing is you're doing sort of a gauge transformed evolution of a Hermitian evolution, of a Hermitian theory, just in this, describing it through this PT theory. Okay. So I finish here. That's the summary. So you can implement indeed this PT symmetry in holography. You can study this correlation functions. You find these instabilities. I think you can learn something. You find that I think there is something to be learned for usual quantum field theory and PT quantum mechanics, and there is some interesting phenomenology, especially when you go to these time-dependent Hamiltonians. Okay, thank you. I'll stop here.
Thank you very much, Karl.
Yeah.
Questions, comments? Daniel.
Yeah. Hi, Karl.
Hi.
Yeah, I have a couple of questions. So when, how do I say this? Yeah, when you talked about this thermal mass, and then you said that instead you would expect to find an instability of the axial fluctuation. So this you had in mind just a model with fermions and the one loop correction.
Exactly. So that's my prediction. If I interpret, the holographic calculation we did in terms of quantum field theory, then I would look to a quantum field theory which has a U1 symmetry, say, but like this axial U1 symmetry, and then I will calculate the thermal mass for fermions, or for these particles in the spectrum. And my prediction is that you would see an additional Hermitian thermal mass term, which would then you would think, you can go further into the PT broken regime because this M5 non-Hermitian term can be larger now because this is still real. If this is a positive contribution, which it usually is. But you should be careful because there's an instability which should show up in the axial charge fluctuations. And you should find here this gamma, this decay rate, if you're in the PT symmetric regime, so that would be a function of this deformation, non-Hermitian deformation parameter. And if you crank that up beyond xi equals 1 in our parameterization, then this should also change to the wrong side of the complex plane and become an instability. So that's a prediction. And in principle, that can be calculated. I think it's not a very easy calculation, but it's also not terribly hard. I think that can be done.
Yeah, but okay, so Yeah, but first, when you're talking about the correction to the mass of the fluctuations, then this is not what you see in the QNMs that you are showing there, no? Because it's exactly the fluctuations.
Yeah. So in the QNMs, what I'm seeing is basically I'm showing the QNMs of the axial charge fluctuation, right?
That's also my other question.
Yeah,
Why is you map those QNMs to the axial charge fluctuation?
I just call it axial charge. It's the symmetry which you use in order to generate the non-Hermitian theory.
Yeah.
Right? Where you analytically continue the symmetry parameter.
Sorry.
Yeah. So I just call it because in the back of my mind I had this fermionic model where it's an axial, but it can be whatever you want. It should be universal, I think.
Thanks.
More questions, comments?
Can I make a short comment? Yeah, so it goes back to the issue of the equivalence of PT-symmetric theories and Hermitian theories. To establish the equivalence, there is no unitary mapping between those two theories. There's a similarity mapping.
Yeah.
Now, in the case of matrices, there's no problem. But in the case of a theory with an infinite number of degrees of freedom, that mapping is unbounded. It's a similarity map that's unbounded. And because of this, the states in the Hilbert space of the Hermitian theory, when you try to map to the non-Hermitian theory, some of those states go off to infinity and don't correspond to states in the non-Hermitian theory. And the same is true with the reverse of that. Okay, so I'm not sure if you can use the word equivalent here. And it's not clear to me that all of the physics of the non-Hermitian theory corresponds to all of the physics of the Hermitian theory. But this is a sort of an open question, and it's not clear to me about that when we talk about that being equivalent.
Okay, yeah, I see. So here, I can only see what we found in holography, and there we found that at least for all the calculations we did, which is, it's a quantum field theory. We have not looked to all the states in the theory. We have just to look to a very small subset, which are the typical things you look at in this holographic setup, like diffusive modes, some simple correlation functions. And so, of course, there's much more which we have not looked at. But to everything we looked at, the correspondence worked. But of course, there are many, many more states in the theory which are probably with high energies and so. So I cannot make, of course, a general statement. I understand that.
I would expect that if there are non-equivalencies between those two theories, they would occur in some sort of extreme limit, either in high energy or in the vicinity of some phase transition or something like that. That's where the unboundedness of the mapping between the two theories might become crucial.
Okay, so you see, I learned already some important point, and we can certainly try to look to this and see if we can see some holographic implementation of this.
Yeah, I would be really interested to see if there is some sort of breakdown in the equivalence where the two theories are actually different, at least in some limit, as I say, like a high energy limit or some non-analytic limit, something like this. But I can't say what I mean specifically.
I see. So you can certainly do things in at least in this time-dependent context. You can certainly do things which you can under no circumstances can do in the in an equivalent Hermitian way. Like you can indeed stay for finite time in this completely non-Hermitian theory, and nothing, the theory doesn't go completely crazy. I mean, you solve these equations and on your computer. If you go too far into this non-Hermitian regime, then the computer tells you stop, right? Certainly you cannot go arbitrarily far. There is a critical value for this psi, even in time-dependent context. But you stay there some time, then you come back and the system settles down and doesn't do anything weird. On the other hand, if you try to give a completely equivalent Hermitian description of this, you cannot do this. There's no way of doing that. You cannot go beyond this because the gauge field becomes singular there, and you cannot do that. So it's certainly true that at least in the time-dependent context, we have situations which are completely different, so they cannot be mapped into Hermitian theories.
But there's sorry, quick question. But when you go beyond the sectional point, of course, there shouldn't be any map.
Yeah, there shouldn't be any map. But the surprising thing is that if in the static case, there is no theory there anymore, right? Everything is complex and so on. But in the time-dependent case, you can go into this regime. You stay there for some finite time, and then you come back, and the theory settles down to a quite reasonable theory. It's not blowing up or anything like this.
Since I interrupted, but you do this at finite t, no?
Yeah, you have. That's also interesting. You have to do that at finite t because, as I told you, when you do these non-Hermitian boundary conditions in the time-dependent case, what happens is that the temperature is actually going down because you violate in the gravity language this null energy condition. So if I start with 0 temperature, I'm immediately running into trouble, and I cannot solve these equations. There, the numerics breaks down like immediately. So we looked, for example, you start at low temperature, you wiggle a little bit in the non-Hermitian direction, and then it turns out that you stay for some time, and then suddenly the curvature blows up and everything becomes singular. So you can lower the temperature to a certain extent, but if you do that too much, if you wiggle too much into this non-Hermitian, if you throw in too much non-Hermitian matter into your system, it does blow up.
Just a comment, in the quantum mechanical scenario, when you have a time-dependent metric, you can map it to an equivalent up to the difficulties Hermitian Hamiltonian, just not by similarity transformation.
Right.
The equation changes.
That's
And you have to add this gauge-like term. I mean, in that context, it's not a gauge transformation. But
it's not a gauge transformation, but it looks like a non-Hermitian gauge field.
Yeah.
And so my interpretation of this is in this simple example is that because you change in a time-dependent way these entrance and exit rates, so usually what happens is the particle enters here, then it tunnels over there, and it goes out. And since in the PT symmetric regime, G is bigger than the entrance rate, on average, you will always have one particle here and here. Right? But then you make this bigger, so more particles can go in, but you don't change the forward and backward amplitude. So you will have some agglomeration here, and here they can go out easily. So you break this careful balance between source and sink. And if you look to what the gauge field is doing in this situation is it adds to this hopping, but in a non-Hermitian way. So you have to balance the forward and backward hopping in a non-Hermitian way just to compensate for this delay, which is now that it's easier for the particle to go in and out and the gauge and this gauge transformation is doing precisely that. That's my interpretation of this.
Uwe and then Miloslav.
Yeah, in natural picture that comes to mind is why not trying? You have this very nice correspondences now on the boundary, this mapping, and if you have this new condition on the boundary, why not go back to the bulk and try to modify the gravitational background in such a way that you can somehow fit these things? Do you think that this is a promising approach, or do you think it's not so good? Because in your approach, for instance, you are already going beyond usual quantum mechanical things of normalizable modes. You have this non-normalizable mode that you are taking as boundary conditions. So you are already much far beyond usual Hermitian quantum systems, because you're including in a natural way via this ADS CFT correspondence in non-normalizable modes. So
Yes.
it's actually it's something like in quantum mechanics, you are leaving the Stokes wedges, the corresponding Stokes wedges, where you have defined boundary conditions at infinity, and you are including other Stokes wedges implicitly by these non-normalizable modes, which are just entering through the gravity sector. And I'm conjecturing, or it might be natural conjecture, when you're looking from this side at your model, just trying to carefully build up all this boundary business, and then forget about the gravity sector for the moment, try to switch to another Stokes wedge in Karl's setup actually, and then to build from this Stokes wedge the gravity background. So you will have a kind of mutual mapping.
Okay. I have to think about that. I'm not so familiar with it.
It seems it could be possible, but I'm not aware whether somebody did this already. Do you know about something like this? Going beyond usual ADS CFT, but some kind of modified ADS or something like this. The important thing is just to have the conformal groups.
Right.
Well,
now you say, I don't know why and for what reason whatsoever, but people start talking about complex metrics in quantum gravity.
Very nice. Okay.
So even Witten had a paper on that. So
who?
Witten.
Recently or
not so long ago? Yeah, I was actually, now I remember you say,
no.
Yeah, probably one should take these complex metrics which you find in this PT program machine. Probably you would also take this more serious.
Another question, just from a side, I might be completely wrong with this rough intuitive picture. Do you know about relations of this? It's clearly not the black hole temperature, but some other temperature that you can relate somehow this ADS CFT duality somehow to Hagedorn transitions. Do you know about something like this, that you have more thermodynamics, more interesting thermodynamics, that you have this, this degeneration growing up so fastly that you are having a transition from this side? Do you know about something like this thermodynamically to plug it into such a geometrical picture? Beyond string theory, I mean, just this phenomenologically.
So actually, this has a precise realization in the ADS CFT correspondence. This is called the Hawking-Page phase transition. Where you actually have a transition. So basically the Hagedorn transition, say if you come from QCD, it's just the number of states grows exponentially as you reach the Hagedorn.
Exactly.
And so in the ADS CFT correspondence, you have and then in QCD, of course, it's not a limiting temperature. You can go beyond it, and then you go to the deconfined phase.
Sure.
Right. So where, all these mesons and so, which proliferate exponentially, then they actually break up. And there, of course, there are models where such phase transitions happen, and where you have, it's actually a phase transition then between empty de Sitter space, where your degrees of freedom are just like mesons and baryons. And a high temperature phase, which is say beyond this limiting temperature, and
it's just a quark-gluon plasma.
Exactly.
Yes. And this is covered by this ADS CFT, or
this is covered by ADS. This is covered. There are models which have these phase transitions. Below the phase transition, you can calculate something like a meson spectrum.
Sure.
And calculate the meson spectrum to some. And above the phase transition, you don't have mesons anymore. You have these quasi-normal modes, and you have plasma physics and this. So that can be done quite explicitly in ADS.
Okay. Thank you for this.
Okay.
Miloslav, you are mute.
I'm trying to see. If I can see the last but one transparency.
Which one?
This time-dependent formula, the gauge before
this one.
Yeah, this one. Yes.
Yeah.
So this gauge transformation is something which plays a role. Okay, so let me first say that it is very nice to see that this holography approach is coming to the game, because precisely this formula in the frame is something where there is close connection with standard quantum mechanics. And the core of the problem is that you normally work in formalism with time-independent eta. And this means that you have sort of analog in Schrödinger picture, where wave function is time-dependent and operators of observables are time-independent. And if you go in standard quantum mechanics to Dirac picture, to interaction picture, so of course you split dynamics, evolution of wave functions, and into evolution of operators. And this is precisely what appears in the form which you denoted by A. This symbol is something which is responsible in analog of quantum mechanics for evolution of operators. And of course, interaction picture is full of interesting questions. So as Karl said, if you go to infinite dimensional spaces, you have a lot of puzzles which appear in Dirac representation. There is Haag theorem and all this kind of non-existence. And this fully analogous to what's happening here. And that's why I think it's absolutely marvelous that this holography approach is taken as a new tool for analysis of this kind of problems.
Okay,
There's a huge area of open questions which appears like that. And it was very nice to see to listen to your talk, because it's really inspiring to see that this connection between gravity and non-hermeticity is taking place. There would be many other questions continuing, but this is the important thing, that once you have this A, it is something which returns you back to quantum mechanics, where those things are more easy to analyze.
Yeah.
So thank you for a talk.
Okay, thank you very much for encouraging remarks.
That would be a good point to finish, but are there more comments, questions?
May I ask a question?
Go ahead, Daniel.
Yeah, so when you said, let me see if I understood, you said you could go for some time into the non-Hermitian, non-PT symmetric region, but how is this different? How you know you're not just exploring the solutions of the static case, where you can also go in the non-Hermitian, in the non-PT symmetric region?
So the difference,
we know they were unstable, but now in a non-equilibrium process, maybe. Because you said that exactly at 0T you cannot do that, and you know that at 0T they don't exist.
At 0T they don't exist. That's true. At finite T, you're right, but they have this instability. I mean, in some sense, if you take this picture that there is this instability, then everything what it says is that you can stay for some finite time. And you go back into the stable region before the mode which grows exponentially really does something very bad to you, right? So, and this is basically, you can see this here in this picture. There are these modes here, for example, this mode. This guy wants to grow exponentially, right? And you have to come back to the PT symmetric regime before this guy does something nasty to you.
Okay, so you're saying that I can understand that when I'm there, it's related to these unstable solutions.
Yeah, well, so the thing is quite complicated, because as you know, there is a limiting value for this psi, depending on the temperature.
Yeah, exactly.
Right? But I think we have not nailed this down explicitly, but indications are that now how far you can go into the, so first thing is, even in this time-dependent setup, if you go too far into the PT program regime, your numeric blows up. So something bad is happening at finite time.
Yeah, and that makes sense with the other picture.
Right. Yes, it makes sense. But the precise value at which this happens is not necessarily the same value what you see if you do this, in this static solution. So this limiting value which you can reach might depend on how fast you run into the PT regime and several other things. So I don't think there is it seems to us from the simulations we did that there is not the universal value, right? That it depends on how fast you run into it, so there.
Okay, yeah, makes sense. Thanks. Sorry for the many questions.
Oh, thank you for the interest.
More comments, questions? Then I would say we thank Karl again. Thank you very much for the very nice talk.
Okay, thank you very much for the invitation. That's very, very interesting and encouraging, I have to say. Thank you.
Could you also send us your slides, please?
Yes, of course. I can.
Brilliant, brilliant.
Yeah.